Hello, am I audible to everyone? Hello.
Yes, sir.
Oh, Urban Mandakini. Okay, I think we can start in a few minutes. Let's wait until 7:15 and then I will start. Okay. Hello, I hope I can start as of now. Uh, so my screen is visible and I'm also audible, I hope. If there is an issue, you can say to me. So I hope everything is working fine. Am I audible?
Yes, sir.
Yes, sir.
No issue. Okay.
Yes, sir.
Oh, no issue. Okay, so in the previous class itself, I discussed four things about a discretization scheme. So the four things which are the four important things about a discretization scheme. One is accuracy, another one is conservativeness, uh, then there is boundedness and transportiveness. Okay, so going to the accuracy itself, so all of us know that when I'm using a Taylor series expansion, where phi of I plus 1 equal to phi I plus d phi dx delta xi and so on. So this expansion, if I actually take this term that phi a equals to phi I plus 4 equals to phi I plus 1 equal to phi I, then I'm actually ignoring the terms which are beyond this term itself. So then what I say is this is first order accurate because the truncation error is basically a function of delta xi. Okay. So if it's a function of delta xi square, then it's called second order accurate. So this is the one which I have discussed in the previous class itself. So there is another form of accuracy, which is how accurately your simulation results are able to replicate experimental measurements. Okay. So this is basically called accuracy. There is another form of accuracy. So what? Because for example, if you are doing a simulation with wrong models and also with a forced grid itself, so you will not be able to replicate the experimental data. So this is uh, another form of accuracy. So there is another term which is called conservativeness. So for example, a flow is happening from left to right across a phase of a control volume. For example, this one is a control volume itself at point P. This one is a control volume, and across a phase of this control volume, the west phase itself, there is some flow happening. So phi at W minus is equal to rho UA, so which is basically kg per meter cube multiplied by meter per second multiplied by meter square, which is kg per second. So that minus at W minus. So W minus means the left hand side of the west phase. So this should be equal to that of the flux at W plus. Uh, so or the mass product. So this one is eventually the mass product, and rho E is a mass flux. So rho UA at W plus. So the left hand side should be equal to that of the right hand side. Okay. So is it clear to all of you? So this is called conservativeness. Okay. So is it clear to all of you? Hello, am I
Yes,
audible?
sir.
Okay. So there is another thing which is called boundedness. Okay. So as we have solved the convection diffusion problem that gamma del square phi equal to 0. So where gamma is basically your diffusion coefficient and diffusion coefficient and phi is basically your any scalar field, any scalar field, V temperature. And for this problem itself, as I have shown numerically also in the previous class by using coding and also by using analytical solution. So what happens that, for example, there is a rod like this. So one rod is one end is at 500 degrees centigrade and the other end is at 100 degrees centigrade. So the profile actually looks like this: 500 degrees centigrade and 100 degrees centigrade on the left hand side and the right hand side respectively. And this temperature profile Tx uh, is basically lying between 100 degrees centigrade and 500 degrees centigrade. Okay. So what happens is that the temperature inside the rod is between the two extremes that we are having at the boundaries itself. So this is basically called boundedness. Okay. So what we have discussed in the previous class also, that if I am actually giving a source term that gamma del square phi plus is equal to 0. Then the temperature profile actually becomes like this, or more accurately like this. So this is 100 degrees centigrade, and the left hand side being 500 degrees centigrade. So what we see is that the temperature at the mid, this point itself, is uh, greater than Px is greater than both 100 degrees centigrade and 500 degrees centigrade. Okay, so this is called unboundedness. So what basically happens is that if I'm actually increasing the source term itself, the more and more the temperature becomes higher than that of the two extremes that we are having at the two ends. One is 100 and the one is 500 degrees centigrade. So even I'm actually writing the matrix equation is equal to B, the source term actually comes in the B matrix. Okay, and higher the B matrix, more is a unboundedness. And if it's pretty much high, if the source term is pretty much unrealistic in nature, so what may happen is that you will not be able to get a converged result, a convergence itself, numerical convergence. So this boundedness is actually one of the things you should be careful of. The source term should not be too much large. Okay. So is it cleared up till now? Hello, am I audible?
Yes, yes.
Okay. So there is another thing which is called transportiveness. So what is transportiveness? Transportiveness, okay, this one. So transportiveness is basically uh, when the flow is happening from west to east, but this one is basically your capital W, capital P and capital E. So P is basically my self-centered of interest of interest. E is basically my east self-centered, and W is basically the west self-centered. Okay, west self-centered. So what typically happens is that my equation actually comes in the format of AP phi P equals to AW phi W plus AE phi E. So there are two criterias for transporting this. Number one, EP is greater than zero, then AW and E should be greater than zero. Okay. Another one is that if the flow is happening from west to east, as said earlier, then EW by EP should be greater than E by AP if the flow is happening from west to east. Okay. Third is that AW by EP should be less than E by AP if the flow is happening from east to west. Is it clear to all of you?
Sir, actually, what this will give, sir?
This will give you one thing is that sometimes what happens is that, for example, uh, AP phi P equal to AW phi W plus AE phi E. Okay, so first of all, I said that if AP is positive, then AW and AE should be positive. Okay, so if AP is positive, and let us assume that AW is negative and AE is positive. Okay, and I basically have a problem like the diffusion problem. At one end it is 500 degrees centigrade, at the other end it is 100 degrees centigrade. Okay, so if I want to find out what is phi E, okay, or phi W, let us say, if I want to find what is phi W, so AP phi P minus AE phi E divided by AW equals to phi W. Okay, so what we are seeing is that AP is positive, AE is positive, phi P is positive, phi E is positive. Okay, AW is negative. Okay, and eventually you will see that in most of the cases, if you are solving a problem, then AP phi P minus AE phi E is positive. Okay, so what happens if the numerator itself is positive by any means and AW is negative, then phi W becomes negative, which is unrealistic since you are having a positive temperature across a length of the rod that you are considering in your problem. So that's what I said is the coefficient should be positive. Okay. So if any kind of discretization scheme you are using and if it is unphysical in nature, then what may happen is that you will not get any numerical convergence. Okay. Another thing I said that if the flow is happening from west to east, then AW by AP should be greater than A by AP. Okay. So we know that our problem is our after discretization we actually get the form like EP phi P plus AP phi P equal to AE phi plus AW phi W. Okay. So what is AW by AP? AW by AP is basically AP phi P minus AE phi E divided by AP, and AE by AP is basically AP phi P minus AW phi W by AP. Okay. So as we can see is that for example if the flow is happening from left to right, then your gradient should be positive in that direction. That is phi W minus phi E or delta phi delta x is positive in this direction, which is phi W minus phi P E divided by delta x W E. So if I put the value in that manner, if it is this one is positive, then if I put the value of phi W here, then this is basically EP phi P minus uh, phi E divided by AW, और डेल्टा एक्स तो बाहर रहेगा और इसमें रहेगा EP phi P minus AW phi W divided by EE. Okay, so your terms become AW by AE, uh, so EP phi P EE E squared phi E minus AP EW phi P plus EW phi W square this one becomes EP phi p minus EW, let's say phi p हो जाएगा, कट जाएगा, so EE square phi E should be greater than AW square, or no, 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 sorry. So if this one is positive, then AW square phi W should be greater than AE square phi E. Okay. So if phi W and phi E are positive, okay. So not only phi W and phi E are basically phi W is greater than phi E. So another safe way is to basically say that AW should also be greater than AE. Okay. Otherwise, what happens? It may happen that the inequality sign is changed. So this one is a kind of safe play. So we can write like this. So this is actually one of the essential criteria which should be satisfied. Otherwise, it may happen is that if AW is less than AE and phi W is greater than phi E, it may happen that this inequality is not satisfied. Okay, it may happen uh, this inequality is not satisfied. Okay, so that's why AW by AP should be greater than AE by AP if the flow is happening from left to right. Is it clear to you?
Yes, sir. Okay.
Okay. So these are kind of simple things that you should keep in mind. Otherwise, what may happen is that you derive the whole thing itself, and then when you are coding it and finding out the solution of it, then what may happen is that you may get some numerical instability and you may not get a convergence. Then you will question the whole discretization scheme itself. So this is actually one of the things you should keep in mind. So
Actually, how we know, sir? Actually, uh, after doing simulation only we have to come to know this, or before that we can avoid this kind of thing.
before this is four condition we should meet. One is conservativeness, transportiveness, boundedness, and accuracy. These are the four things that I've said. So these are quite simple things to follow. So while after doing the, I will show in one case is that if the transportiveness is not maintained, so what may happen if the coefficients are not positive? But there are certain things which may happen even after you follow four of them. Okay, so that you have to say by after doing the simulation itself, you have to verify and say that see that whether it is unstable or not. Okay, so it can happen due to some unphysicality in the solution also. Okay, you have taken some wrong boundary condition or something like that, which will violate the other things also over the period of time. So these things I will show you as of now by while deriving the discretization scheme, or if you are planning to create a discretization scheme of your own. So these are the four things you should keep in mind. But when you are actually going for a full-blown simulation, there are other factors which come into play that you will learn with experience. Okay.
Okay, sir.
So as previously said, if it's a convection diffusion problem. So what I did was actually I derived by using central difference formula. Central difference formula. Okay. So what I will do is basically do a kind of recapitulation. So for example, if it's a convection diffusion problem, so d rho dt plus del dot rho u phi equal to gamma del square phi plus source. Since this one is a convection diffusion problem, source term is zero, temporal term is zero. So only the convective and the diffusion term is there in the equation. So after that, this del dot rho u phi dv should be equal to gamma of del dot gat phi dv. So after kind of simplifying that n cap rho ua, sorry, rho u phi dA. So after applying the Gauss divergence theorem, Gauss divergence theorem. So this should be equal to n cap dot gradient of phi dA. Okay. So what you have to do then is that we take a sample control volume like this. This one is basically your P control volume. This one is east and the left hand side is west. So what you're doing is basically you are evaluating this integrals at the uh, at point P and point W, small w. So this small e and small w is basically the cell phase at between the P cell centroid and the E cell centroid, whereas small w is basically the cell phase between the capital W and the capital P cell centroid. Okay. So what you have to do is that this is basically rho u phi a at east phase minus rho u phi a at west phase equal to there should be a comma, sorry. So gamma grad phi at west and Aries area at east phase minus of gamma grad phi area at west phase. So if I'm using the central difference thing, so we know that rho phi UE. So it should be so rho phi uh, sorry rho UA. I can keep it out of the bracket phi E minus rho UA west phi W equals to gamma grad phi east A minus of gamma grad phi west A. So then I can write rho A. So rho UA is basically, or I can cancel the area from both sides. Rho UE phi E minus of, so if I cancel the area, it becomes a flux term. So gamma grad phi east minus of gamma grad phi west. So rho UE is basically what? Fe, and rho UW is what? FW. So as we know that since we have to maintain conservativeness, so Fe should be equal to that of FW. So both of them should be equal. Okay. So rho EE, so Fe, and this phi we can use write as phi P plus phi E divided by 2, and then FW multiplied by phi E plus phi W divided by 2, and this gamma phi E minus phi E divided by delta X minus of gamma phi P minus phi W divided by delta. Okay. So if I actually convert this into AP phi P equals to AW phi W, AW phi W plus AE phi E. So then I can write it as AP equals to, or AW equals to DW plus FW divided by 2. Okay, so gamma by delta X, I'm calling it as uh, D uh, E, and this gamma E by delta X and gamma W by delta X, I'm calling it to be DW. Okay, so if gamma is spatially changing, then gamma E and gamma W has significance. But if it's not spatially changing, we can consider this to be gamma E equals to gamma W equals to gamma. So I don't think that will make a difference. And then this AE is basically equal to DE minus AP divided by 2. And then there is AP. So we always know that AP equals to AW plus AE plus AP minus AW. Okay. Since we know that conservativeness is actually one of the thing which is maintained in our case, So this AP is, must be equal to that of FW because of conservativeness. Because of, because of conservativeness. Okay. So if I look at it carefully, so I've talked about conservativeness. So if the flow is happening from west to east, AW should be equal to AW by AP should be equal to that of should be greater than E by AP. Okay. So the coefficient should be positive. So what we are saying is that AW should be positive. Since AW is positive and DW is positive, so gamma is positive, so gamma by delta x itself is positive. And FW is what? Rho u at W. So since the flow is happening from west to east, the flux itself is positive also. So that's why this AW term is by default positive. But if I go to the AP term itself, sorry, the AE term, this is not by default positive. There is a certain condition that should be maintained in order to make it positive. Okay. So is it clear to all of you? Hello, am I audible?
Yes, sir.
So, so I think Arpan is there in the class, right? Arpan is here, Pandafin is here. So is it clear to all of you? Pandya,
Yes.
Sweta,
Yes, sir. Yes, sir. Yes, sir.
okay. So it is easy for me if you say it yes, otherwise I have to ask everyone individually. So it's better that you are responsive. So AW is by default positive. There is a certain condition I have to allow in order to make it positive. Similarly, if AW and AE is positive, by default EP is positive. Okay. So D should be greater than AE divided by 2. That means what? Gamma E divided by delta X P minus of rho E divided by 2 should be greater than 0. So this one is greater than 2. So this should be gamma by delta X is greater than rho E by 2. Then rho U by gamma by delta X is greater than 2. So Peclet number greater than 2. Okay. So am I doing anything wrong? No, no, no. Sorry. I'm doing something wrong. So this rho E by gamma by delta X should be less than 2. Okay. So Peclet number less than 2. So if Peclet number is less than 2, then your A is positive. Okay. So this is called Peclet number, which is basically your convection by diffusion. Convection by diffusion. If it is calculated from for in each and every cell, then it is called cell Peclet number. P is silent, so cell Peclet number. So for example, if it's a convection diffusion problem, so a solution basically looks like this. Like it's a bit parabolic kind in nature. So if the value actually ranges for phi equal to 1 to phi equal to 0, so it is bit parabolic in nature. And if Peclet number is, for example, 0.2, you will get a curve like this. So if its Peclet number is greater than 2, so if the analytical solution is somewhat like this, or the correct solution, phi equals to phi equal to, ranging from phi equal to 1 to phi equal to 0. So your solution basically looks like this. It will kind of oscillate, start to oscillate. If Peclet number is some 5 or something like that. So numerical stability, instability kicks in when Peclet number is greater than 2. Okay. So this scheme is stable if Peclet number is less than 2. So if the Peclet number is greater than 2, then it will kind of blow up. Okay. So is it clear to all of you?
Yes, sir.
Okay. So this is actually one of the things you should keep in mind. I will also share the program with you. So then you will understand that if I change the Peclet number to be too much, then we will have some numerical instability. So in order to remove this problem, we actually introduce our point scheme. Pandiatas, do you have any question?
No, sir. No, sir.
Okay. So there is another scheme which is called the Affine scheme. I hope many of you have heard about this. This scheme I started in the previous class. So if, for a minute, if I have a problem for you, we can solve it together. Let us give us a general format. I think that will be. So, for example, if the flow is happening from west to east, and this one is a west cell centered, and this one is a p cell centered, and this one is a east cell centered. So this one is a east cell phase, and this one is a west cell phase. So uh, rho u phi at east minus of rho u phi at west equal to gamma d phi dx east minus of gamma d phi dx west. Okay, so I'm directly writing the equation. I'm not using the cos divergence theorem. I'm showing you all the steps which are we should use in order to get to this equation. So what we are doing is we are directly using the final equation. Okay, and then we can directly put the phi e and phi w, where phi e and phi w is basically expressed as a function of phi p, phi capital P, phi capital E, and phi capital W. And then we create a system of algebraic equation, linear algebraic equation. Since we know that we are going to solve this equation at the cell center, so we have to express the value at the cell base as a function of cell center. Okay, so this term is pretty much easier, the right hand side term. So which is basically the central difference formula in your case. So this one is gamma phi p minus phi p divided by delta x minus of gamma phi p minus phi w divided by delta. So this is a simple central difference formula. And then what we have to do is basically if the flow is happening from west to east, then phi small p should be equal to that of phi capital P, and phi small w should be equal to that of phi capital W. Okay. So this small e and small p should be same, and this capital W and small w should be same. Okay. So if I put it in the equation itself, so this one is basically your phi p minus of rho e phi w, capital W, and this is equal to gamma phi e minus phi p divided by delta x minus of gamma phi p minus phi w divided by delta. And then if I actually see the coefficients of phi p itself, so rho e plus gamma by delta x plus of gamma by delta x, and if I actually go to phi w also, then it becomes rho e plus gamma by delta x, and going to the coefficient of phi e, that is gamma by delta x. I hope I am right. So you can see the coefficients are by default they are positive. So AE is positive, gamma by delta x. AW is positive, which is rho e plus gamma by delta x. And AP is also positive, since it's a combination of E and AW. Okay. So is it clear to all of you?
Yes, sir.
Okay. So uh, then if the flow is happening from east to west, if the flow is happening from east to west, capital E, capital P, and capital W, and this one is small e and small w, then you can do the derivation on your own, but I'm just giving you the hints how to do it. So then phi small e is equal to phi capital E, and phi of small w is basically equal to phi of capital P. Okay, so then you have to use this equation as rho u phi of small e minus of rho u phi of small w equal to rho u phi, sorry, gamma of d phi dx at small e minus of gamma of d phi dx at small w. So phi e minus phi p divided by delta x is minus of gamma of phi p minus phi w divided by delta x. So this one is phi u rho u phi capital E, and this rho u phi capital E. Then you kind of simplify it, and then you can use it in the way you like. So uh, so your equation actually becomes d plus dw minus of aw. This ap is basically equal to dw aw plus de fe a. Now you can think that the coefficients are turning out to be negative, but my positive axis actually tends from west to east, and therefore F is basically negative, and FW is also negative, since the flow is happening from east to west, and my X actually extends in this direction. So my positive X direction is actually from west to east. So therefore, since this one is negative, so this one becomes positive. This term is also positive, and this is negative, so this term is also positive. Since this D and dW are basically positive, irrespective of the flow becoming which is coming from east to west, it doesn't matter. Okay. So since this FW is negative, so minus of FW is positive. So this whole thing is positive, and this one is negative, as I have written uh, below this term, and therefore this one should be positive. Okay. So as we have said earlier that transport is actually one of the things violated in case of central difference formula. So now what we did was actually we tweaked the formula in such a manner that the transport is basically obeyed in our case. Okay. So now we may be hoping that this is actually one of the things we should always obey. But there are some problem in this case also, so which we are going to discuss in the subsequent case. So another thing, I hope I'm clear until now. Am I clear until now? Hello, am I audible?
Yes, sir.
Okay. Uh, you can ask me questions. It is
Sir, this
okay, please. Hello,
sir once again repeat this one, sir.
which one?
Sir, once again repeat, sir. Last sir.
Uh, last thing, what is?
East to west direction. West
Ah,
to east direction we need to repeat, sir.
west to east direction. If it is happening, then Fe and Fw is positive. If the flow is happening from east to west, then Fw and Fe actually becomes negative. If these things are negative, then you can see that AW, sorry, this should be phi P, and this should be phi W, and this should be phi E. So then you can see that A, AW, and AP, three terms are basically positive. That's what I was saying. That even if I change the direction, the coefficients remains positive. Is it clear to you now?
Yes, sir. Yes.
Okay. So then what we are going to do is that, for example, since we want to write it in a direction invariant format, so we can write it like this also. So if it is like AP phi P equals to AW phi W plus AE phi E. So this AW is basically D plus max F comma 0, and A is D plus max, 0 comma minus A, and AP is AW plus AP, AW plus AE plus AP minus AW. Okay, so you can use this max function in your program also, and that's why I've written like that. So as I've shown you how to solve the problem by using central difference formula in the convection diffusion problem that I've shown you by in the previous class itself by using octave. So what you can do is that if you want to solve it by using this, what should I say, this half-point scheme, what you have to do is basically you have to change the value of A, AW, and AP, and then you can create the same program for that of the half-point scheme. Okay, so the whole thing remains the same. So then, if there are 5 cells in the domain, so 1, 2, 3, uh, this 4, and this 5. So this is delta X, this is delta X, this is delta X, this is delta X by 2, and then this one is basically this one is delta X by 2, this one, and this is. Okay, so as of now, let's ignore these things. So we actually have 5 control volumes over the whole domain. So as you can see here, 2, 3, and 4 are basically your internal cell centers. So as we have derived earlier, what we do is basically we find the equation for the internal cell centroids, and then what we do is actually we go to the boundary cells one by one, and then we are kind of create a matrix of our own, which we can solve by putting the value of D and F itself, and then we can get the temperature profile over the whole room by using the points. So what we are doing is that, let me check whether the recording is happening or not. So then what we can do is basically this equation, if I write it carefully, for p equals to 2, the equation is 2d plus f multiplied by phi 1, phi 2 equals to d plus f multiplied by phi 1 plus d phi 3. Similarly, for p equal to 3, uh, it is 2d plus f phi 3 equals to d plus f phi 2 plus d phi 4. Similarly, for p equals to 4, it is 2d plus f phi 4 equals to d plus f phi 3 plus d phi 4. Is it clear to all of you? You can basically put this thing in the equation itself, this thing, and then find out the coefficients. Okay. So if the flow is happening from west to east, so max of this will be equal to 0. If the flow is happening from west to east, this should be equal to what? F. So AW is D plus F. So this one. So A is basically what? D. AW is what? AP is what? AW plus AE. AP minus AW is basically equal to 0 because of conservativeness. And this D plus F plus D is what? 2D plus F. So which actually appears here, since we are actually solving for the p equal to 2 cells and all. So your p value is what? 2. Your base value is what? 1. So 1 is basically your d plus f, and then your east value is what? D. Okay. This is A, this is AW, this is AP, and E is what this, which is basically D. So is it clear to all of you?
Yes, sir.
Then what we
Yes,
have
sir.
to do
Yes,
is
sir.
so what you have to do is basically you have to find out the equation for that of the boundary cells. So this one is 1, this one is 2, and this one is uh, east, and this one is west. So west corresponds to your TA. So T is basically, or phi A. So phi is basically the value at the boundary, the westmost boundary. So this one is given in the problem. Okay. So what you have to write is basically if E phi E minus if W phi W equal to gamma E d phi dx at E minus of gamma W d phi dx at W. Okay. So this is equal to if of phi 1, since E is basically equal to 1, so phi E equals to phi 1, if the flow is happening from west to east, and your phi W is basically phi A. Okay, so this becomes f of phi 1 minus f of phi A equals to gamma E phi 2 minus phi 1 divided by delta x minus of, similarly we have to use gamma 2 gamma by delta x phi 1 minus phi A. Okay, similar to the one we have done for the central difference formula. Okay, so we are using the forward difference formula here. Forward difference. This one is central difference order of accuracy is delta x squared, which is second order accurate. This one is delta x, which is first order accurate. Okay. So now this equation can be kind of simplified. So this becomes a plus pd phi 1 equals to d phi 2 plus a plus 2d phi a. So this one is d gamma by delta x, as I have said earlier. So is it clear to all of you?
Yes, sir.
If you want to derive, I can give you some time so that this equation doesn't appear in front of you abruptly. So if you want to make yourself comfortable, you can take some time from me, maybe some 5 minutes in order to derive the equation on your own. So do you want to do it or the tempo is fine with you? Hello, am I audible?
Yes, sir. You can continue, I think.
Okay. So then this one is 4, this one is 5, and this one is a east face and this one is a west face. Okay. So this east face corresponds to TB, which is or phi b, the value of the scalar field, the value of the uh, scalar field at eastmost cell center. Sorry, eastmost at the eastern part of the rod here. Okay. So this thing is basically equal to F phi e minus of w phi w equals to gamma of d phi dx at east minus of gamma of dou phi dou x at small w. Then this becomes f of phi phi. Since f and f w are equal, we can directly use it. And this f of this phi of small w equals to phi of 4. So f of phi 4 is equal to 2 gamma by delta x phi b minus phi phi minus of gamma by delta x phi phi minus phi. Okay, this we can reduce at f plus 3d phi phi equals to f plus d phi 4 plus 2d phi b. Is it clear to all of you?
Yes,
Hello,
sir.
am I? Okay. So this equation can be further modified into Ax equal to B format. So U is basically what? Phi 1, phi 2, phi 3, phi 4, and phi 5. Since this one is a column matrix, so AC equal to R or Ax equal to, let us write as Ax equal to B, otherwise you will confuse. X equal to B. So this one is X. Okay. So B is basically your 2D plus A, phi A, 0, 0, 0, 0, 2D, phi B. Okay. And this A is basically A plus 3D minus D, 0, 0, 0, minus D plus A, 2D plus A, minus D, 0, 0, 0, minus D plus A, 2D plus A, minus D, 0, 0, 0, minus D plus A, 2D plus A, minus D, and then the 0, 0, 0, minus A plus A, and this one is A plus 2. Oh, sorry, 3D. Is it clear to all of you?
Yes,
Hello?
sir.
Okay. So I'm giving you some 10 minutes break. So you can have a look at the things that I have taught you. Then after 10 minutes, I will start again. Okay. Is it okay to all of
O-
you?
Okay, sir.
Uh, I hope I am audible to everyone. My screen is not visible. I have to activate it. So, first time, start now. Let's see. Yeah, the recording is happening. Am I audible to everyone? Is my screen visible?
Yes, sir.
Uh, I think we can start as of now, or we should wait for a few minutes for that. Uh, Let us wait for a few minutes. Mm. So, as I discussed earlier, so uh, central difference scheme and uh, central difference scheme and point scheme we have discussed as of now. In today's class, I have shown you the derivation of both. So now we are going to study another scheme which is called the quick scheme. So there are some problem associated with the point scheme also, which I am going to discuss in the next class. But as of now, I am introducing another new scheme which is called the quick scheme. So this scheme is basically third order accurate. So quadratic upstream interpolation for convective kinetics. Convective kinetics. Okay. So what we are going to do is basically we are going to increase the accuracy of the offense. So one of the things that I discussed in the previous class itself is that my screen got frozen, I think. Let me unshare and share again. Stop sharing. Then I should share my screen. Uh, Arpan, is my screen visible?
Yes, sir. Again, it went off.
But now it is visible.
Yeah, now it's okay.
Okay.
Yes, sir, now it's okay.
Yeah. So in order to increase the accuracy of the pointing scheme, so what we have to do is that we have to take more points. So that I have discussed earlier also. So if I want to express it as a function of more points, the order of the accuracy actually increases. That I have derived by using the method of undetermined coefficients. So more self-centered needs to be included. So if the flow is happening from uh, west to east, which is in the positive flux direction, so then is I minus 1 self-centered, I self-centered, and I plus 1 self-centered. So what we do is that we take two self-centered upstream and one self-centered downstream. Okay, and we assume that the profile actually varies as a function of x square. So a naught plus a2 x plus a1 x plus a2 x square, where a naught, a1, and a2 are the coefficients that we have to determine. That I will show you how to do it. So for example, If x equal to 0, origin actually starts from here. So this one is delta x by 2. So what you have to find out is basically what is the value at phi x at delta x equal to delta x divided by, and also the value of d phi dx at f equal to d phi dx at x equal to delta x divided by. Okay, is it clear to all of you?
Sir, the purpose of taking 2 points upstream, that means we are giving more focus to the direction. That is why, right? That is the purpose.
Yes, more transport.
Like
Okay,
more weightage is given so that like direction.
yeah, more weightage is given so that your transport is increases. Okay, so then what you have to do is basically you have to find out the value of the coefficients. Okay, so how to find out the value of the coefficient? For example, this is I minus 1, and this is I plus 1. Okay, so then this phi x is basically what? And your origin actually starts from here, x equal to 0. So in the right hand side direction that is positive, in the left hand side direction that is negative. Okay, so phi x is equal to a naught plus a1x plus a2x square. Problem is that because of weak internet, the things are not showing up in the screen. Is it visible to you, Arpan? The things that I'm writing on the screen?
Yes, sir.
So what equation I've written on the screen? Phi x equal to a naught x plus a naught plus a1x plus a2x square. Now it is visible. So therefore, set x equal to 0. So phi x is basically what? Phi I x equal to delta x. Phi x is basically what? Phi I plus 1 at x equal to minus delta x. Phi x is what? Phi I minus 1. Okay. So is it clear to all of you? So phi I equals to a naught. Phi I plus 1 equal to phi I plus a1 delta x plus a2 delta x square. And phi I minus 1 equal to phi I minus a1 delta x plus a2 delta x square. Is it clear to all of you?
Yes, sir.
Okay. So phi I plus 1 plus phi I minus 1 equals to 2a 2 delta x square plus 2 phi I. Okay. So a2 is basically equal to phi I plus 1 plus phi I minus 1 minus of 2 phi I divided by 2 delta x square. Okay. So what you are doing is basically you are adding this equation 1 and 2, and instead of a naught you are basically putting phi I. Okay. So then third equation is basically, so what you have to do now is basically you have to uh, subtract the equations in order to get the value of a1. So 2a1 delta x. So a1 is what? Phi I plus 1 minus phi I minus 1 divided by 2 delta x. Is it clear to all of you?
Yes, sir.
Okay. So phi x is basically what? Phi, let me lose the speed and infinite address. So phi x equal to phi I plus phi I plus 1 minus of phi I minus 1 x by 2 delta x plus phi I plus 1 phi I minus 1 minus of 2 phi I x square by 2 delta x square. Is it clear to you?
Yes, sir.
So then what I have to do? I have to find out phi a and d phi dx. If at the surface I have to find out the value of the variable and also find out the value of the derivative of the variable. So phi f is what? At x equal to delta x divided by 2. So since I have to find out the value of the variable at the surface, so phi I plus phi I plus 1 minus of phi I minus 1 divided by 2 delta x divided by 2 plus of phi I plus 1 plus of phi I minus 1 minus of 2 phi I divided by 2 delta x square divided by 2. So this is equal to phi I plus phi I plus 1 minus phi I minus 1 divided by 4 plus phi I plus 1 plus phi I minus 1 minus of 2 phi I divided by 8. So this is equal to phi I 1 minus 2 by 8 plus phi I plus 1 1 by 4 plus 1 by 8 plus phi I minus 1 1 by 8 minus 1 by 4. So this is equal to 6 by 8 phi I plus 3 by 8 phi I plus 1 minus of 1 by 8 phi I minus 1. Is it clear to all of you? Hello, am I audible?
Yes, yes, yes. Okay.
So I think there is an issue in the internet, and that's why he's kind of delaying. Let us. So then, what I have to do is basically I have to find out the value at the cell phase. So this is basically equal to ddx of phi I plus phi I plus 1 minus of phi I minus 1 2 delta x multiplied by x plus phi I plus 1 plus phi I minus 1 2 phi I divided by 2 delta x square and this x square. This is equal to d phi dx at f equal to phi I plus 1 minus of I minus 1 divided by 2 delta x and plus of phi I plus 1 plus phi I minus 1 minus of 2 phi I divided by delta x square multiplied by x. Then this is equal to so at the surface itself, for example, if this one is basically equal to x equal to delta x divided by 2, so this becomes phi I plus 1 minus of phi I minus 1 divided by 2 delta x plus of uh, phi I plus 1 plus phi I minus 1 2 phi I divided by 2 delta x. And this, if I simplify, it will be phi I plus 1 minus of phi I divided by delta x. So this order of accuracy is basically delta x square. Central difference. Okay. Is it clear to all of you? Hello, am I audible?
Yes, sir.
So now let us see what is the order of accuracy of the convective scheme. Okay. So we know that phi f equal to phi a plus d phi dx delta x divided by 2 plus of d square phi dx square delta x divided by 2 square dq phi dx cube delta 1 by 3 factorial delta x divided by 2 whole cube. Okay. And there should be a half term also in front of it plus higher order terms. Okay. So if I actually simplify it, so phi f equal to phi I plus a1 delta x divided by 2 plus a2 delta x divided by 2 square. So if I compare this thing, we will see that that is actually third order accurate. So dq phi dx cube is basically your leading term error. Leading term error. Okay. So convective scheme is basically convective scheme is third order accurate. Diffusive scheme is second order accurate. Overall accuracy is third order. So I've said earlier also that if there are two schemes, one is second order, another one is third order accurate. So the overall accuracy is third order. We generally take the higher order accurate. Okay. And you will see is that if I increase the grid point, if delta x decreases and number of cells increases, it will go towards third order accuracy. Okay. And on the other hand, if delta x increases and your in cells decreases, that is the number of cells in the domain decreases, then this one is going to become second order accurate. Second order accuracy. Is it clear to all of you? Hello, am I audible?
Yes, sir. Yes, sir.
Okay. So then what I'm going to do
Sir,
is
is it
basically
possible for the polar coordinate also?
for the polar coordinate. Generally, if I go for the polar coordinate, the Taylor series expansion changes a bit. That can be done for the polar coordinate, but most of the solvers that we write is basically in Cartesian coordinate system. Okay. So,
Okay.
so
But
what
sir, but
happens?
sir, I mean that is it possible to central difference formula लग सकता है क्या polar coordinate में भी?
हाँ कर सकते हो मतलब you can do it but what we do is basically we kind of solve the whole equation in xy coordinate system and then उसको vx को vr v theta vz मतलब vx vy और vz को vr v theta and vy में convert कर देते हैं. Okay, because in Cartesian coordinate
Okay,
system the
sir.
formulations are a bit easier and that's why we kind of stick to Cartesian coordinate.
ओके सर सर आई मैं कैश एंड फ्लूइड में हम आर टी आर एंड जेड का है अगर हम उसमें सेंट्रल डिफरेंस फॉर्मूला लगाएं तो उसमें भी पहले हमें कार्टेशियन में चेंज करके फिर करना होगा
नहीं तुम पोलर का पूरा लगाओ ना मतलब पोलर में तुम लगा रहे हो तो बेसिकली उसमें क्या होता है तुमको सेल साइज वगैरह सेम रखना पड़ेगा बिकॉज फॉर एग्जांपल if I actually take a sphere like this and if I want to simulate a rotational field so my domain gets divided the cells actually becomes a radial one. Okay, so So this is cell 1, this is cell 2, this is cell 3, this is cell 4, cell 5, cell 6, and cell 7, and cell 8. So then you have to take this control volume like this. So then your dr and d theta are basically different. So you have to write the equation in such a manner. Okay, the whole equation, and you have to use a Taylor series expansion for the polar coordinate system. So I'm basically going for the
Okay,
Cartesian and
sir.
the Higgs cells, but if I'm going for this kind of unstructured kind of thing, then actually you have to use certain kind of measures which are kind of different from the one I'm teaching.
Okay, sir. Sir, I want to use the FDM in the cation fluid. That is the equation with the R and the Z.
Pardon the Z. Then if I find any material, I can share it with you. That how the formulation works.
Okay, sir.
Okay. So,
Yes, sir. Thank you,
so
sir.
okay. So, Arpan, do you have any question?
So this question came up about coordinate transformation. So will it also involve use of Jacobian if if in any case if we want to use like polar coordinate or something
Yes, yes,
in our code,
yes.
Jacobian.
That you have to use. So,
Hmm.
if I find any material, I will share it with you, or I can discuss in the next class also. Okay.
Yes.
So, if I take a cell centroid like P itself, similar to the one that I've discussed previously. So, since I've said that I'm going to take two cell centroids in the upstream direction and one cell centroid in the downstream direction. So east is basically your cell centroid in the downstream direction, and small w and ww, which is west cell centroid, are the two cell centroids in the upstream direction. So what I'm going to do is basically I'm going to discretize this convection diffusion problem. So Fe phi e minus 8w phi w equals to gamma e d phi dx at small e minus of gamma w d phi dx at small w. Okay. So then phi f is basically what? Minus of phi I minus 1 by 8 plus 6 by 8 phi I plus 3 by 8 phi I plus 1. Similarly, phi E is basically what? Phi W divided by 8 by 6 by 8 phi P plus 3 by 8 phi E. Similarly, if I write the equation for phi of small w, minus of phi WW divided by 8 plus 6 by 8 phi W plus 3 by 8 phi P. So d phi dx at face is basically equal to phi I plus 1 minus phi I minus 1 divided by delta x. So d phi dx at east is basically equal to phi e minus phi p divided by delta x. So d phi dx at small w, since we know that the derivative we are founding is basically happening according to that of the central difference formula, so we can directly use that in our case. So then the equation becomes Fe minus of or write it like 6 by 8 phi p minus plus 3 by 8 phi e minus phi w by 8 minus of fw 6 by 8 phi w plus 3 by 8 phi p minus phi ww divided by 8. So this is equal to dE phi p minus phi p minus dw phi p minus phi w. So this is equal to phi p 6 by 8 fe minus 3 by 8 fw plus dE plus dw. Okay, so this is phi w fe by 8 plus 6 by 8 fw plus dw plus phi e minus 3 by 8 ap plus de minus 5 w by e. Okay. So is it clear to all of you?
Yes, sir.
Okay. I hope we can stop here. Not too much content for a single class itself. We can also convert this into AP 5P equals to AW 5W plus E 5E. So it will require some kind of manipulation, by the way, algebraic manipulation, which I will do in the next class. So I hope it is okay until now. Okay?
Yes.
Okay. Goodbye.